In mathematics, the category of topological spaces, often denoted top, is the category whose objects are topological spaces and whose morphisms are continuous maps or some other variant. For example, objects are often assumed to be compactly generated. This is a category because the composition of two continuous maps is again continuous. The study of top and of properties of topological spaces using the techniques of category theory is known as categorical topology. NB. Some authors use the name top for the category with topological manifolds as objects and continuous maps as morphisms. As a concrete category, like many categories, the category top is a concrete category, meaning its objects are sets with additional structure and its morphisms are functions preserving this structure. There is a natural forgetful functor U, top set to the category of sets which assigns to each topological space the underlying set and to each continuous map the underlying function. The forgetful functor U has both a left adjoint D set top which equips a given set with the discrete topology and a right adjoint I set top which equips a given set with the indiscrete topology. Both of these functors are, in fact, right inverses to U. Moreover, since any function between discrete or indiscrete spaces is continuous, both of these functors give full embeddings of set into top. The construct top is also fiber-complete, meaning that the category of all topologies on a given set X forms a complete lattice when ordered by inclusion. The greatest element in this fiber is the discrete topology on X, while the least element is the indiscrete topology. The construct top is the model of what is called the topological category. These categories are characterized by the fact that every structured source has a unique initial lift. In top, the initial lift is obtained by placing the initial topology on the source. Topological categories have many properties in common with top: limits and co-limits. The category top is both complete and co-complete, which means that all small limits and co-limits exist in top. In fact, the forgetful functor U, top set uniquely lifts both limits and co-limits and preserves them as well. Therefore, limits in top are given by placing topologies on the corresponding limits in set. Specifically, if F is a diagram in top and is a limit of UF in set, the corresponding limit of F in top is obtained by placing the initial topology on. Dually, co-limits in top are obtained by placing the final topology on the corresponding co-limits in set. Unlike many algebraic categories, the forgetful functor U, top set does not create or reflect limits, since there will typically be non-universal cones in top covering universal cones in set. Examples of limits and co-limits in top include: the empty set is the initial object of top. Any singleton topological space is a terminal object. There are thus no zero objects in top. The product in top is given by the product topology on the Cartesian product. The coproduct is given by the disjoint union of topological spaces. The equalizer of a pair of morphisms is given by placing the subspace topology on the set theoretic equalizer. Dually, the co-equalizer is given by placing the quotient topology on the set theoretic co-equalizer. Direct limits and inverse limits are the set theoretic limits with the final topology and initial topology respectively. Adjunction spaces are an example of push-outs in top. Other properties: the monomorphisms in top are the injective continuous maps, the epimorphisms are the surjective continuous maps, and the isomorphisms are the homeomorphisms. The extremal monomorphisms or the subspace embeddings. Every extremal monomorphism is regular. The extremal epimorphisms are the quotient maps. Every extremal epimorphism is regular. The split monomorphisms or the inclusions of retracts into their ambient space. The split epimorphisms or the continuous surjective maps of a space onto one of its retracts. There are no zero morphisms in top, and in particular the category is not pre-additive. Top is not Cartesian closed since it does not have exponential objects for all spaces. Relationships to other categories. The category of pointed topological spaces top is a coslice category over top. The homotopy category HTOP has topological spaces for objects and homotopy equivalence classes of continuous maps for morphisms. This is a quotient category of top. One can likewise form the pointed homotopy category HTOP. Top contains the important category house of topological spaces with the Hausdorff property as a full subcategory. The added structure of this subcategory allows for more epimorphisms. In fact, the epimorphisms in this subcategory are precisely those morphisms with dense images in their codomains, so that epimorphisms need not be surjective.